Thanks for hanging on here. In this final video for the section, we'll draw some tight connections between rank and the singularity, or lack thereof, of a square or n by n matrix. So for this entire conversation, unless I say otherwise, A will be not an arbitrary, but will be an n by n square matrix. Let's suppose momentarily that A is row equivalent to the n by n identity matrix. It may not be, but let's suppose it is. If it is row equivalent to the n by n identity matrix, then we showed in the last video that since it's row equivalent, it's equivalent, and therefore their ranks are the same. And therefore, if A is row equivalent to the identity matrix, then the rank of A is equal to the rank of the identity matrix, and the rank of the identity matrix is n. If you haven't seen this yet, then you should stop the video and prove to yourself that the identity matrix definitely has rank n. Remember, the rank is the dimension of the row space or the dimension of the column space. So just take the identity matrix, say take a 3x3 or a 4x4 to make it concrete, and write out the rows of the 3x3 identity matrix, for example, and convince yourself that the dimension of that row space is 3. So we've shown that if A is row equivalent to the identity matrix, then the rank of A is equal to n. Conversely, let's now suppose that the rank of A is equal to n. Now we can take A and take it all the way down to reduced row echelon form. And let's call that matrix B. But now if B is the reduced row echelon form of A, then A and B are row equivalent, and therefore the rank of A is equal to the rank of B. And so if rank of A is n, then the rank of B, the reduced row echelon form of A, is n as well. So now we have a matrix B, which is in reduced row echelon form and has rank n. It then follows that B can't have any 0 rows. For assume for the moment that rank of B was n, and that B was an n by n matrix with a 0 row, say down here. Then what's the rank of B? Well, it's the dimension of the row space. If you have n minus 1 rows up here, the dimension of the space spanned by these things can be at most n minus 1 if you have this 0 row. So with a 0 row, it would be impossible for B to have rank n. And so we conclude that if B has rank n, it can't have any 0 rows. And now we go back and invoke, I think it was fact number 7 in the first video in this unit in our review. That fact was, if B is a matrix in reduced row echelon form with no 0 rows, then B must be the identity matrix. Let me just pause and comment that this fact may seem almost obvious. It does require some proof, and if you can't quite see how to do it, I suggest that you pause and think about it carefully. It may take you a few minutes to convince yourself that this fact must be true. We are not proving it right now, not because it's immediately obvious, but just because we're relegating it to an exercise. We're not proving it right now, but we are using it. So, to summarize again, we're supposing that the rank of A is equal to n. We take A to reduced row echelon form to B. Then B has rank n as well, since they're row equivalent. We conclude that B can't have any 0 rows. Therefore, we have a matrix B, which is in reduced row echelon form with no 0 rows. And so we know that A, in fact, is row equivalent to the identity matrix, since we've shown B to be the identity matrix. And this is our last main theorem of this section. If A is an n by n matrix, then its rank is n if and only if it is row equivalent to the identity matrix. The language that is often used is the following. If A is an n by n matrix with n rows and n columns, then we say that if A has rank n, then we say that A is full rank. Now, to conclude, I'll just list a collection of 4 corollaries which follow almost immediately from this theorem and some of the previous results. using some other facts that we know about non-singular matrices. So for these corollaries, A is an n by n matrix. Then one can prove that rank of A is equal to n if and only if any of the following hold. First, rank of A is n if and only if A is non-singular. Second, rank of A is n if and only if the determinant of A is non-zero. Third, rank of A is equal to n if and only if the vector equation or matrix equation Ax equals b has a unique solution for any b. And the last corollary doesn't exactly fit into this pattern, so I'll list it on its own. This last one, the last one, rank of A is less than n if and only if the homogeneous equation Ax equals 0 has a non-trivial solution. So you should sit down and write down the proof of each of these corollaries, refer to the textbook, which has the proofs of some of them, and some of them are relegated to exercises. If you're stuck on one of them or you'd like to talk about it, I encourage you to post to the discussion forum so we can talk about these. There's a lot of theory in this chapter, so please talk about it with yourselves, on the discussion forum, with someone. Conversation is very important to make this stuff stick. It's a very powerful exercise to try to explain the proof to one of your classmates or to somebody else. Let me make a few concluding remarks before we're all done here. One of my concluding remarks is this: you should definitely do this exercise, which I'll describe to you now. All of the conditions equivalent to non-singularity. So we've seen this condition of non-singularity crop up and appear in many different contexts, and you should take out a clean sheet of paper and begin the following list. A matrix, a square matrix, A is non-singular if and only if what? There are many conditions. The determinant of A is non-zero. The rank of A is n. The rows of A form a linearly independent set of vectors. Blah, 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 blah. There are at least 5 or 6, I think a few more, other conditions which are equivalent to non-singularity and which go a significant way towards tying all of the theory that we have learned in this entire class into one page. Non-singularity is a notion that unites just about everything in an amazing way. So please do that. I think that's done near the end of this section, but you should definitely make your own list. Another thing I did not cover at all in these videos is some of the geometric significance behind the row spaces and the column spaces and the null spaces. Your text does talk about that briefly. It's very interesting to see the geometry behind these various subspaces. We didn't talk about it at all here. It is in there, but we are short on time. So I hope some of this helped. Again, please post questions and discussions to the forum and let me know how it goes. Good luck.